Now, in this last section of Lecture 3, we're going to look at repeated sampling. And before we jump too deep into that, we're going to look at some examples that won't necessarily look like they apply at first, but we'll find some new premises out of them that make cause for us to have some new rules. And those rules that we'll establish will be the rules of repeated sampling. So the first example we'll look at is related to poker. So the first question that we can ask is, how many unordered 5-card poker hands are there? Well, the word unordered in this problem is kind of giving it away because, as you may recall, the unordered version is combinations. So there are a total of 52 cards in a poker deck. So we can say that n is equal to 52 as just a global rule for this specific problem. And we're choosing 5 cards, and the order doesn't matter. So this is purely combinations. So we can write this as the number of combinations where we have 52 elements for n, and we are choosing 5 of them, which we can, as you may recall, also write as 52 choose 5, which is equal to 52 factorial divided by the product of 5 factorial, and in this case 52 minus 5, or 47 factorial. And we'll find that that is equal, after we crunch the numbers, to 2,598,960. Just a few possible hands. The next question gets a little bit different, and we'll kind of stretch ourselves a little bit here. And that is, how many poker hands are there where all of the cards are the same suit? So in any poker hand, there are 4 different suits, and each of those suits are made up of 13 values, or different faces on those cards, as some may call them. And so those values are going to be like an ace, a 2, a 3, up to a 10, and then your jack, queen, and king. And all of those are the 13 different values within a poker deck. And again, like I mentioned, there are 4 different suits as part of that deck. So going back to our question here, how many poker hands are there where all of the cards are the same suit? Well, we can look at this as a 2-phase process. The first phase is to pick a suit. And so in that situation, we can say that there are 4 different suits. So phase 1 has 4 options. And as you may recall from the basic counting principle, anytime we have multiple phases, we multiply the results together. So we'll have 4 times something. So now that we've chosen a suit, we have 13 possible values within that suit. And so we will say that we are picking 5 that are all of that same suit. So in this case, it's going to be 4 times the number of combinations for 13 as our n for this case, because there are 13 total values available within a suit. And we are selecting or choosing 5 of those. So in this case, we end up with 4, again, the first phase of selecting a suit, multiplied by n choose k. We're choosing 5 cards out of a 13-card suit. Multiplying all that out, we find that this is equal to 5,148 hands, where all of those cards are of the same suit in that 5-card poker hand. The next question that we'll look at is, how many poker hands are there where there are 3 cards of one value and 2 cards of another value? This is in poker what we call a full house. And to do this, we'll also use our basic counting principle, but we'll also use some of our sampling rules that we've looked at previously. And so what we'll see is that we can pick the 3 cards of one value and 2 cards of another value. But the way to look at this is, again, a phased operation. So in the first phase, we are going to pick a value, and in the second phase, we are going to pick another value. Then after we've picked both of those values, we're going to pick 3 cards of the first value and 2 cards of the second value. So this is actually a 4-phase operation at the end of the day. So in the first phase, we're going to select a value. And there are, as we said earlier, 13 values. So phase 1 has 13 options. Now, again, because this is a multi-phase operation based on the basic counting principle, we're going to multiply these values together. In the second phase, we're going to pick another value, the value for the 2 cards that will be in this hand. And in that case, we've already selected one value out of our 13 possible, so there are only 12 values remaining for the second value that we pick. After that, we'll go back and look at either one of them really, but let's just say the first value for the time being, and we're going to pick 3 cards out of the 4 that are available. Now specifically, this is 3 suits out of the 4 suits that are available within that value that we selected earlier. So in other words, we're doing a combination again. We're asking for 3 out of the 4. How many different ways can I create an unordered set of 3 suits from the 4 suits that exist? So this is going to be, as our third phase, the combination where n is equal to 4 and k is equal to 3. Again, because we are picking 3 cards of one value. Then our last phase is to pick 2 cards of another value, and that's going to be the combination of 4 choose 2. Again, we're only picking 2 cards, but there are still 4 suits available. Now, when you multiply all of this out, you'll find that this value right here, this 4 choose 3, will resolve down to 4 possible combinations, and that the 4 choose 2 has 6 possible combinations. And again, when you multiply all that out, you'll find that there are roughly 1.6 million, or 1,617,408 possible poker hands where there are 3 cards of one value and 2 cards of another value, which is actually pretty high when you get right down to it, considering that there are 1.6 million out of 2.6 total million card sets that result in a full house. So the odds are in your favor, as it were. Now, this begs another question, which is, what happens when I'm picking the same thing more than once? And that brings us to this concept of repeated sampling. And we're going to generalize it first, and then we're going to look at some specific examples. So the first statement here that we'll make is that we have a sequence S. And if that sequence has n items, and within those n items there are n sub 1 identical objects of type 1, n sub 2 identical objects of type 2, and so on, all the way up to n sub t identical objects of type t, then we'll say that the number of orderings of S is just n factorial divided by n sub 1 factorial multiplied by n sub 2 factorial multiplied by n sub 3, n sub 4, all the way up to n sub t factorial. And so we're going to kind of use this equation to our advantage and say when we repeat, when we have things that are sampled more than once, that we can just use this equation. So looking at a practical example, we may ask the question, how many unique strings can we form from the word Mississippi? So in this case, we have a sequence of characters that form this word Mississippi, but you'll notice that there are repeated elements. The S's, the I's, and the P's all show up more than once. So for our equation that we just looked at, we would say that if there are n sub 1, n sub 2, all the way up to n sub t different values that are repeated that number of times, that we would just put those here in the denominator. And again, the equation's in the bottom right-hand corner for reference. But the first thing we would need to evaluate is, well, what's the total n? And the total n for the word Mississippi is 11. There are 11 total characters in the word Mississippi. Then let's say that rather than n sub 1, n sub 2, all the way up to n sub t, we just do n, and then the subscript is the letter that we're looking at. So n sub m, or the number of m's in the word Mississippi, is just 1. And N sub I, or the number of I's in Mississippi, is 4. N sub S, again, the number of S's in the word Mississippi, is also 4. And N sub P, or the number of P's in Mississippi, is equal to 2. So based on this formula, we can go ahead and just insert some numbers and plug and chug. So what we're left with is how many unique strings can we form from Mississippi? Well, the answer is 11 factorial divided by n sub m factorial, or 1 factorial, n sub I factorial, or 4 factorial, n sub s factorial, again 4 factorial, and n sub p factorial, or 2 factorial. And when we break all of that out and plug in those numbers for factorials, we'll find that there are 34,650 unique combinations or unique strings that can be formed from Mississippi. Now, that's a fairly small number. It's an approachable number compared to what it would be if each of those were considered to be separate elements. If all those were separate elements, then we would just have 11 factorial. But because there are repeated elements, we have to reduce based on this denominator here. Why does that matter? Well, these S's here, we can swap. Doesn't make a difference on what the outcome is because they are the same identical element. Now, let's look at a slightly different example and say that we're at a library and there are 8 books available. And we want to know how many ways those books can be divided among the 3 students that are there. And we'll call them Amy, Bill, and Claire. So let's assume that Amy has to get 3 of those books, Bill has to get 3 of those books, and Claire has to get 2 of them. Well, in this case, it's also repeated sampling, right? Amy is sampling 3 times. She's there 3 times. Bill is also there 3 times, and Claire is there 2 times. So in this case, the way that we would look at this problem is how many total books are there? There's 8. Well, n is equal to 8 then. N sub A, or the number of books that Amy will get, is 3. N sub B, or the number of books that Bill will get, is also 3. And N sub C, or the number of books Claire will get, is equal to 2. And in this case, we just plug all these numbers into a formula and we find that we are left with 8 factorial divided by 3 factorial times 3 factorial times 2 factorial. And plugging all those numbers in, we find that that is equal to 560 unique ways that we can divide those books among the 3 students.